good evening, everyone. Thank you for coming out. This is the first session of Astrobiology Graduate Conference 2017. It's very exciting. Thank you, Brett, for helping to lead the charge on this one. What I'm going to introduce to you guys today is a session that has been lovingly called the Building Planets and Listening to the Songs of Their Peoples session. And so what I'm going to do is introduce you to the schedule. There is a slight change. Emilio is actually currently in transit, so his talk is going to be bumped to just before the winning PWR presentation. So Ryan Loomis, if you're in the audience, if you can come get mic'd up, yeah, that's you. Ryan's going to take it off as soon as we get done with this intro talk. But as you can see, we're kind of all over the map here. We've got some SETI, we've got a couple of talks about disks, and then we've got planets orbiting white dwarfs, and then we've got some education with the coherent content storyline on exoplanets. Now, it seems like these are all very disparate ideas, but I want to assure you that in the grand scheme of astrobiology, no idea is too far-fetched to find a home. And as you can see here on this lovely diagram of this entire session, the universe and the galaxy and the solar system starts off as some nebulous cloud, condenses down to a disk, we get a star. That star lives for some 10 billion years or so and then explodes and dies and leaves us with a white dwarf. Now, just to put all of the talks into some sort of context, we think that somewhere in here we might find some intelligent life form that may want to communicate with us if we're cool and don't panic. The idea here is that you also need to worry about how disks form and evolve, because that's how planets form and their host stars, around their host stars. And we're also going to hear about white dwarfs, which is the sort of terminal endpoint for low-mass stellar objects throughout the universe. And then we're also going to figure out how you might teach this stuff, how you might introduce it to an audience of either your peers or more likely an audience of middle school to high school students. And so just to put some names on here, this is sort of the breakdown for who's going to be talking about what. Now, because I uploaded this before the last minute schedule change, it's going to be slightly out of order. So I'm going to introduce you to the SETI talk first, which is based on some work that's being funded through the Breakthrough Listen project, which has devoted about $100 million over the next 10 years to try to find aliens. Now, the way they're doing it with modern technologies is, for example, the 100-meter Green Bank telescope, which is, as I understand it, the largest steerable radio antenna in the world. The largest steerable structure in the world. That's crazy. And then some smaller ones, but who cares about those? So those are the current technologies. No, we don't care about you either. So those are what we're currently using to try to find these radio signals that other intelligent species might be sending out. We're also using something called LOFAR, which is the low frequency array that's looking for similar transmissions from other types of objects. And together, these current technologies are really trying to reach out and touch something like the nearest 100,000 stars in the system. And if this works, okay, so we're going to take a small tour just to give you an idea of the sense of the scale of the SETI search. So obviously, this is the sun. It's a pretty cool sun, you might say. And then that's the solar system, to give you a sense of scale. I'm not entirely sure why airplanes are touchstone for speeds. Obviously, Voyager is the farthest flung human innovation in the history of the Earth, as far as we know. And so that's 1 light year. You can see that the Oort cloud is just a tiny little speck in the middle of the screen of this. Oh, I'm sorry, the Oort cloud is a speck now, because you're starting to look at some of our nearest stars. Come on, one more. So that's sort of the local neighborhood. These are some of the brightest stars in the sky, generally. and some of the dimmest ones too, because you can't actually see them with the naked eye in some cases. And then if we pause it here, this is the nearest 100,000 stars in the sky. That's a lot of places to knock on people's door and see if anyone's home. Brett. I got it. Okay, so like I said, they're looking at something like the nearest 100,000 stars, which is a lot of real estate, and not just with the current technologies, but also with several new arrays that are coming online in the next couple of years, or tens of years. For example, the next generation Very Large Array, or the Square Kilometer Array. These are very large radio telescope arrays. And the one I believe we're going to hear about today, assuming that Emilio actually does make his travel plans, is going to be some work from the Low Frequency Array, LOFAR. Two of the talks in this session are going to be about disks. So here's a lovely JPL rendering of what we might see if we were actually able to get close enough to one of these disks. Thankfully, we don't have to rely just on JPL animations. We can actually observe these out in the wild. This is HL Tauri, an ALMA image, and this is Elias 227, which shows that lovely spiral arm structure that we tend to associate with galaxies, but it also shows up in smaller scale features like protoplanetary disks. Now, one of the really cool things about these disks is that they tend to be exceptionally short-lived, and this is showing you how many stars at what age have a disk, for example. So most stars that are fairly young, a few million years old, 80 or 90% of them tend to have disks, and then as you get past between 15 and 20 million years, most of the disks have gone away. So a lot of the planet building action occurs in an incredibly short amount of time. And there's a lot of complexity, a lot of richness in how these disks evolve. And then we're going to hear about two different aspects of disks in terms of visualizing them and then modeling them with these magnetohydrodynamic models that couple the stellar magnetic fields with disk interactions to figure out how you might initiate either gap formation or enrich a location in material that you can form planets with it. Like you can see the gaps here and the bands. So the gaps can either be cleared by planets that are forming in that region, or they can be cleared by magnetic field interactions with the disk. And so there's a lot of really rich material in here that you can sort of delve into, and you get different chunks of that disk depending on what you observe it with. Now, to go to one of the other talks in our session, we want to figure out where white dwarfs live. And so this is the famous Hertzsprung-Russell diagram. This is the main sequence here. The sun is sitting prettily here. It's about a G2 star. Now, as the sun evolves, it will evolve into the Giants class, and then it'll shoot over here and then down onto the white dwarf track because it's a smaller star. Anything about a few solar masses tends to evolve down onto the white dwarf track. Anything larger than that turns into a black hole, which is harder to observe or not as interesting, at least for the context of the session we're talking about today. And white dwarfs can start off really, really, really hot, like tens of thousands of degrees, even up to, one literature survey suggested, up to about 150,000 degrees when they start out. But they cool relatively rapidly in that initial phase, and then they sit around the 5 to 10,000 degree range for a few billion years as they cool off towards that background temperature of the galaxy. And one of the things you can see here is that for a white dwarf at a similar temperature to the sun, it has a similar black body spectrum. So you might expect that it would be kind of like living under the sun. And that just shows you the evolution of the habitable zone. Time is marching upwards in this diagram, and the distance to the host star is here. In this case, it's the white dwarf. And so I just want to point out that this tick mark here, 0.005 AU, is equivalent to 1 solar radius. So that means that if you had a main sequence solar type star, and you had a terrestrial planet literally parked in its envelope, and then that star exploded and that terrestrial planet managed to survive, it would find itself in the habitable zone of a white dwarf after about 1 billion years. And so there's a lot of complexity in how you find planets, well, not in how you find planets, but how you get planets to be that close to their parent stars after such a cataclysmic evolutionary event for them. And just to point out that these white dwarfs are incredibly small as well, so they're bright, small, and that's why their habitable zones are so close in. And one of the last talks we're going to be hearing about today is the Danny Beringer's talk about the coherent content storyline, which involves some elements from education, including the claim, evidence, and reasoning strategy, where you make a claim about some result of an investigation, and then you try to back it up, and then you tie together those claims and that evidence. And this is all part of the next generation science standards, which looks at connecting scientific practices with core ideas, and then sort of tying that into a broader context with these cross-cutting ideas, these cross-cutting concepts. And the cohesive content storyline is all about making sure that when you're telling someone a story about a scientific event or concept, that the context in which you provide them that information all feeds into that main point, and all feeds into that rational discussion about that concept. And after the session, but it's sort of in the same session, we're going to hear a little bit more about the proposal writing retreat, which is a workshop that brings together a number of students. It's actually 25 participants this year in 9 different groups that wrote proposals that range from a spectropolarimetry catalog for exoplanet surface characterization to the characterization of the solid geyser effluent and approach for Enceladus. So lots of crazy stuff that's being suggested as potentially interesting for your peers. And we'll hear more from that from Becky, I believe, later. And so with that, I would be happy to take any potential questions you might have. First off, the answer is going to be 42. And then if you don't know or didn't catch it, and that goes for this whole conference, ask. All right? So I'll take questions.
I'll bring you a mic so you can be heard by the streamers.
Brett, you get to be co-chair. And then Bradley can be the other one. Yep.
Yeah, you mentioned the SETI project, the 100,000 stars. Does anyone have like a rough estimation of how many like planets within that set?
I'm sure someone does, but I think it's a large enough sample that it's going to follow the occurrence rates from Kepler. So, you know, M-star planets. Did you have a? You have a question? So it's going to follow Kepler statistics. So, you know, about roughly a third of the M stars will have planets, and then, you know, roughly a quarter of the G-type stars will have planets. So terrestrial planets in their habitable zones, I should say.
Scale, order of magnitude.
Order of magnitude, they're probably going to be anywhere between 10 and 30,000 terrestrial planets in the habitable zones around the nearest 100,000 stars.
Cool, thank you.
Yeah. All right.